people here?
Yes.
Can you read it? You still didn't understand my writing? It's perturbations in fluids.
Sorry for that. About it here.
This should be readable. Perturbations in fluids, sound, turbulence, and instabilities. It's a long topic that we'll cover in a couple of lectures.
Sorry for that.
You are excused. Alright. What do you mean by perturbations? Small disturbance. I am sitting far away. You are part of the class or you are?
Yes, I'm part of it.
Sit here. My voice is not that good, it will not reach there. You will struggle.
I'm just already connected.
It's up to you, but you will not listen to me properly. Anyway. Perturbation means small disturbance in the system. Okay? What happens when you disturb a system? If the disturbance is very small, the system will remain stable. Okay? Example being, take water in a pond, throw a small stone. When you throw a small stone in the water, the perturbation caused by stone is very small. So the perturbation is very small because pond is very big. What happens to that? It perturbs the surface and the perturbation spreads onto the water surface. But the water remains like it doesn't become sea, right? No waves erupt. So the perturbation, if it is very small, sometimes it cannot disturb the whole of the system. Okay? What it means? It means the perturbation decays with time. But this is not always true. There are cases where if you perturb the system, the perturbations grow with time. What happens if it grows with time?
It will be stable.
System becomes unstable. Okay? That we will cover in instabilities. However, there are certain conditions, generally very high Reynolds number, that we talked about in last class. When the Reynolds number is very high, or this watery or the fluid is moving very fast, the fluid, every fluid has perturbations always. Small perturbations are always there inside, and they keep on decaying, so the fluid remains stable. However, if the Reynolds number is very high, the perturbations keep on growing and the system becomes turbulent. Okay? If the perturbations increase, they make the whole system unstable. Okay? So today we will discuss those perturbations which are small and they do not disturb the system, do not destabilize the system. When you put a small perturbation in the system, the perturbation propagates within the system with the speed of sound. Okay? So today we will cover the first one, sound. Give me a practical example where you perturb a system and the system is destabilized. Not just fluids, any. Does it happen if I perturb slightly? Like if I poke finger at the wall, whole wall will collapse. Does it happen?
Yeah, like a ball on top of a hill.
Hmm?
The simplest example is like a ball on top of a hill. That
Yes.
a little perturbation will fall
It
down.
will increase. Okay? That's an unstable system. But the perturbation is from outside. Right. If I put a coin like that, if it's pointed, it will come up. I give a crude example sometimes. If you have a cow and you slap a cow from behind, the cow will just wave her tail and then it will stabilize it. That means the perturbation decays with time. However, if you take a pin, needle, and prick it, you will see the system has become destabilized. It will run away. It can happen. That we will see in the last part of this topic, okay? The instabilities. Now let's come to the first topic. What is sound? Sound is whatever you are hearing from the
Pressure wave. A pressure wave.
Pressure density, pressure.
Yeah.
Technically speaking, there is a medium between you and me, which is air. When I'm speaking, I'm perturbing the system here, causing some perturbation, compressing the air slightly, changing the pressure and density. Now that perturbation propagates in the medium and reaching your ears. So today we will study the dynamics of how this perturbation propagates and reaches your ears. So let's assume a very simple system. So now we are starting the first topic, sound. Let's assume a box, more or less like air in this room. It's uniform, with uniform density rho 0, okay? And the pressure is also uniform, P0. Uniform. Okay. The way I'm speaking, suppose in between, at some point, you cause a perturbation at any point. You cause a perturbation, the density in the system changes slightly. Previously it was rho 0, and this small perturbation, rho prime. The pressure also changes like this, P0 plus P prime, with the conditions rho prime is much smaller than rho 0, and P prime is much smaller than P0. Okay? Very small perturbations. So you perturb the system at one point. What happens to the perturbation? That's the problem we are dealing with. Okay. So we come back to the equations. Yeah, something?
Wait, can you explain please
Yes.
what is perturbation?
Perturbations, okay. We are dealing with perturbations. If you disturb the system, any system. Perturbation means the disturbance is much smaller than the stability of the system. Very small disturbance. When I'm speaking, I'm perturbing the system here. Small perturbations. Perturbations can decay with time. Means the system is stable. Sometimes the perturbations grow. You go to the beach, right? You see small waves, they keep on coming and then colliding, and then you get huge waves. Perturbations are great. For the perturbations to grow, it has to take energy from somewhere. But that we'll deal with in the last section, instabilities, after a couple of lectures. Inside the fluid, sometimes the perturbations automatically grow and the fluid becomes turbulent. That we also deal with in maybe next lecture. Now we are dealing with the small perturbation in a stable system where perturbations grow. Okay? Not grow, they propagate. That is sound. So we assume the system with uniform densities and pressure rho 0, P0, and then we applied some small perturbation, which is much smaller than the uniform values of the densities and pressure. Okay? Now our problem is what happens to these perturbations. We know the answer, it propagates. It goes from my mouth to your ears, everywhere. But we want to deal with it scientifically, mathematically. So how do we do that? We come to the equations of motion. Whatever we derived, okay? Mainly we have two equations, continuity and Euler equation. Now fluid is not viscous, we don't care about viscosity. It can be, but we keep the system simple so that we understand the process. Continuity equation. What is rho here? Rho is not rho zero, rho is density after perturbation, and pressure is the density after perturbation. And what is V here? Is V zero? The fluid is uniform, static in the beginning. Before perturbation, the fluid system was static and stable. What is V here? Is V zero? What is V? V is the velocity of the perturbation. There is no velocity in the fluid, but when I speak, there is velocity here. You remember we dealt with the oscillating object in the fluid in one of the sections. The velocity was the velocity of the perturbation. So how the fluid is perturbed. So the perturbation is moving in the beginning. So the V is velocity of the perturbation, and V is very small. Because the perturbation, if the speed of perturbation is very high, it's a non-linear perturbation. These approximations don't hold them. So it's important. V is velocity of perturbation or perturbed fluid. Okay. And we have Euler's equation. Okay. Now we put the values of density and pressure from here in the equation of continuity. So we reach it.
What is rho prime?
Rho prime is the perturbed density. When I speak, the density is slightly increased. Previously the density was rho zero. If I do this, slightly it's pressure. So increases the density. Whatever the perturbation you put. Okay. Can be positive, negative, density can increase, decrease, doesn't matter. So this rho zero is constant, so del rho zero del T is 0. Only this survives. You open this. Which terms are 0 here? This is definitely 0 because rho 0 is constant. There is no gradient. It is cause of that. Now, all terms are non-zero. However, we can see that this is a second order term. Why? The perturbed density is anyway very small first. Then your velocity, which is small velocities of the perturbation. So small value multiplied by small value, it's a second order term. It's very small compared to this term. So this is rho 0. compared to this term. So this is second order term. Similarly, this is also second order term. Okay. So these are close to 0. Close to 0 means they are much smaller than this term. So we are left with only the first term. This term, so I write this here. Okay. The equation number 1. This is the continuity equation for the perturbation. Okay, I can remove this. Now we play with Euler equation. I can say this is the second order term. Velocity. Velocity is small, and 2 velocities here. So for the perturbation, this term is not significant. Okay? We get rid of this term. And we can put the values of pressure and density from here. This. So we apply. Okay. Now the gradient term has 2 terms, P0 and P prime. Gradient of P0 is 0 because P is uniform. So we are left with only this term here, and in the denominator, with this condition, only rho 0 survives. So we write this equation here. Okay. Now the system, if it is closed, it's a adiabatic system. If it adiabatic means system is not taking.
If it is,
We
then
keep the
it's-
system isolated, closed.
Ah,
Closed system is not always adiabatic. It can extend like a closed box. So term is not completely correct. System can be adiabatic if it is isolated from surroundings. But even if the system is adiabatic or not adiabatic, the perturbation we assume can be adiabatic, okay? Because it's small perturbation given. So in the place of the local region of the perturbation, we can assume the perturbation is adiabatic. But if we impose that the system is also adiabatic as a whole, then you can assume that the pressure is a function of density. Then we can expand the pressure in Taylor series. Around density. Because I said the system is adiabatic, entropy has to be constant. It's a Taylor expansion. So what is P? P is P0 plus P prime. And P0 is cancelled. We are left with P prime equals, and what is rho minus rho? 0. So rho prime. So P prime is rho prime. We put this in equation 1. There. What is rho prime? Rho prime is P prime over del P over del rho at constant entropy. So we put this, okay? This in equation 1. I write this equation here, little bit rearranging. Call this equation 3. I just multiplied with this denominator, and this is constant. It's a partial derivative, so it comes out of the differentiation, and multiply our equation goes here.
Can you explain again what is the deal with the absolute value?
Here,
Yes.
okay. If the system is adiabatic, pressure is a function of density. Okay. Pressure is a function of density. If pressure is a function of density, and then you disturb the system, for small perturbation, you can expand the perturbation in Taylor series. You might have studied in mathematics, right? So that's what I did. You expand it around P0 pressure. What is the final pressure? It is pressure equals initial pressure plus perturbed little bit. So it's dp d rho, adiabatic system constant entropy, and rho minus rho 0. So basically you expanded the function around rho. Then there are more second order terms that we don't care about. This is what it is. Now rho minus rho 0 is simply rho prime. That's what it is. And P is, what is P? It's P0 plus P prime. The P0 cancels from both sides. It's gone. It's only P prime. Got it? Clear?
Yes, thank you.
Okay. Then we put the value of rho prime from here, P prime over this, and then use this value directly in here, equation 1. Putting it here is just simply solved. It's a partial derivative, comes out, multiplying del rho prime, and this derivative comes here. That's it. Yes.
Why doesn't it change in time?
What?
The p to the rho.
Because it does not change in time because it's constant entropy. This is rate of change of This is typically unit of state. Right? So in constant entropy system, the pressure is only function of density. The perturbations do change in time, that you will see it there. The derivative of pressure with density does not. So it simply comes out. So you have only the perturbation that changes with time. The perturb part is much smaller than that. Because you see it here, the pressure is this plus this plus this. This is why for diabatic systems, when the entropy is constant, or maybe the perturbation is negligible, what we assume is that this derivative is negligible. But this does, and that's what our purpose is, how the perturbations propagate with time and space. Okay? Now, we see these two equations, equation 2 and equation 3. Because we have shown pressure in terms of density, we have only two parameters to study here, velocity and pressure. So these two equations in combined form show the behavior of sound propagation. But can we understand something from here? No, it's still complicated. It's not, we know it's a sound, sound is a wave. Nothing seems like a wave here. So we'll further deal with that. But these two equations completely satisfy sound, its propagation, in time and in space, it's a gradient. Now, consider curl of V is 0. It's not an automatic condition. V can have curl. Again, what is V here? Velocity of the perturbation. So if I perturb the velocity here, how can I make sure that its curl is 0?
No turbulence? No turbulence?
There is no turbulence, but not necessary that if you don't have turbulence, there will not be curl. Perturbation goes like that. It can have curl. If we don't know it, it can have or not. But when you look at this equation here, equation 2, Euler equation, if you ignore the second term V dot grad and take the curl of this equation 2, curl of equation 2, okay, take the curl. This is 0 in fact. Okay. And when you impose that the system is static, it is still, it does not mean it is 0. Curl of V is not necessarily so. Here it turns out that curl of V is constant. Okay. So you can have a constant curl. The thing is, curl cannot remain constant in time. If you perturb the system, the perturbation propagates. So it's not a trivial assumption, but in general, we'll see its consequences in the final interpretation that the curl is 0, the sound waves become longitudinal. Okay. So if you assume it is still not completely general. If we assume the perturbations do not have a curl, then V can be expressed as grad phi. Phi is velocity potential. We know it. Then we put this in equation 2 and 3, use it. Then we will obtain the wave equation. Put in equation 2. This is rho 0. Okay. Now rho 0 is constant. We can take it inside the gradient because it's anyway constant. And I can integrate it on left and right hand side, and the gradient vanishes. So what you have is rho 0 del phi del t equals p prime. Okay. Now we obtain p prime here. I can put this because I put the value of velocity or the expression of velocity in equation 2. Obtain this expression. Now I put this in equation 3. Put in equation 3. You have to put velocity here as well, right? It's not, it's this expression. So basically this is del dot del b del phi 0. Rearrange it a bit. Density comes out and goes in 0. Del square phi over del t square plus del p over del rho constant entropy del square phi equals 0. Now this is wave equation. Does it look like a wave equation? So we obtain this equation finally. Can you recognize this, how it looks like?
What did you say about the minus sign
Minus sign?
in the integral?
Here?
Yeah.
Oh, it has a minus sign. Okay. So we put it there. And it has a minus sign. Okay. Okay. That was it. Does it look like a wave equation? Wave equation in phi, in perturbation. Second derivative in time, second derivative in space. And you haven't studied wave equations. Have you studied waves in classical mechanics?
Yeah.
Oscillations in waves. You may have studied waves in electrodynamics too. Maxwell's equation. Solve the Maxwell's equation. You get wave equations for magnetic fields and electric fields. You're not familiar with that, but doesn't matter. We will see very soon when you solve this equation to get solution like the way. So with all these assumptions we finally obtain the equation if it is one dimensional. It's one linear. Let's say wave is propagating in x-axis. Okay. When I was speaking, the wave can propagate only in one direction. In that case, the gradient simply becomes double derivative of x. And the equation becomes minus c square here c is square root of at constant entropy. This is a problem. C is the speed of sound. Generally C is the speed of light, but here C is the speed of sound. You can call it CS as well. This is the wave equation, one dimension. It's a plane wave. Why it's called a plane wave? Because it's propagating in XZ plane, YZ plane. Traveling along x-axis, the plane YZ. It is propagating along x-axis. It's propagating along y plane. This is the propagating along x-axis. Okay, what else? It's a longitudinal wave because curl of V is 0. Longitudinal means what? There are two types of waves: transverse waves and longitudinal waves. Electromagnetic waves are transverse waves. If we talk about fluids, the gravity waves, when you put a small stone, small particle or small pebble on water, waves are produced. Those waves are transverse. Transverse means in wave something is oscillating and propagating, right? Wave means there is some oscillation, the oscillation is propagating. So if the propagation is along x-axis and the wave is propagating along the perpendicular to that, these are called transverse waves. And you can see the waves on the surface of water by putting small pebble, those waves are transverse waves. Wave propagates along the plane of the water, but the oscillation is perpendicular. When you impose, that is, it's conservative situation, it's called conservative condition, like del cross V, it's irrotational. Sound waves are longitudinal. Understandably, when I put the density pressure here, density increases and it propagates. Oscillation is also in the direction of motion of the wave. It's not perpendicular. So these are called longitudinal waves. So longitudinal waves. Sound waves are longitudinal. Okay, now we solve this equation. And the solutions are very general. It's a mathematical problem, right? It's a mathematical equation. You have to solve this to find the value of phi. It's very general. Mechanical waves, electrodynamics, everywhere the same solution is applied. before you proceed and solve this, I saw that not many people are submitting the assignments. Was it too difficult?
There was a question there I submitted, but question 3 in the assignment, last assignment, was a bit unclear, I have to say.
Remind me which question?
To derive some equation from another, I think 144.
Derive the expression of velocity from the formula from the relative Stokes law.
So many questions.
I
I didn't bring this.
Incorrect unless you redefine the constants. So
Which constants?
A and B.
Show me the equation 44.
You need to derive
Okay,
those
you
two
derive this
from
one?
this. No, you have to derive those two from that one.
You get separate solutions for A and B if you try to match them with 145 and 146.
Okay, whatever you get, you just write it, okay?
Even if I get two different definitions of B.
Okay, write it and then we'll solve it in the class if it doesn't work, okay?
Okay.
Did you try this one?
It works. I think it works if this equation has A divided by 2. I think it works.
Yeah, the coefficients here not seems to be incorrect. I think I got
There are boundary conditions, I have written it, but did you try equation for 143?
What?
Did you try this, the previous one, the 143 equation?
So just get two separate definitions for the constants and tell you that's what.
Oh, that was a bit tricky too. I have to say, in general, I think most of us didn't understand that part of the lecture last time. Maybe it was because we were a bit tired after the exam and our concentration a bit was a bit limited, or just was unclear.
That topic was not derived in very much detail like we are deriving everything here. Because it was just I wanted to give you the idea of how it works.
I think we were a little bit lost in the algebra last time.
But this is still straightforward. Like deriving equation 143. You have to solve this.
Yeah, but you asked about it in the homework. Why you threw off those coefficients, the other components. It was a bit tricky, but yeah.
I think you get 4 terms in the answer. Some people solve it. You get 4 terms.
Yeah.
First and second term is some r square.
Yeah.
Second term is r. Third is 1 by r.
Cost here.
Fourth is constant.
Yeah.
Okay, so you get 4 terms. 2 of them has to be 0 for this to be correct. Okay, that's where I wanted you to think about. You knew the boundary conditions. There was the 2.
One gets cancelled because it doesn't change anything because it has no
That's the potential.
R in front of it, and one is because it's when R goes to infinity, that term explodes, and
That's it. 2 terms we can see like that. If r goes to
cancel
infinity.
out.
I'll square them.
No, the coefficients are 0.
Yeah,
If r equals to infinity, f has to be 0. Okay, so when you get a term like f is equal to a r square plus br or something like that, plus something.
Plus C plus D divided by R.
So these 2 terms are 0. Means the a and b has to be 0.
That's
no,
it.
B.
A.
I don't know, but you get
You
4
still
terms.
have the R in one.
I'm not talking about a. Let's call this q and p. Okay, because I don't remember the
B is
terms.
not necessarily 0 because
You
you
don't
get
know.
that.
The term that is not multiplied
The
by R.
constant can be thrown off because it's a potential. It's used.
Okay,
This
r
is
square
the
term was
potential.
0 because of the boundary conditions.
Yeah, and R
Okay.
isn't 0.
But R doesn't have to be. You have a constant like R in 0
Mhm.
that you can throw off because it's used as a potential.
Right, but r square was 0.
Yeah, R squared is 0.
Okay, just mention it in one line.
Also, it wasn't clear in question 1. You said
Question 1 is the most important question.
question 1 part 3.
Use the solutions obtained in point 4. I have
Yeah,
no
point
idea
4.
what point
It's
4
not
is.
point 4, it's
We're
point
trying
1.
to guess.
It's
Ah,
point
Yeah,
1.
it's point
Right.
I make many mistakes, okay?
Yeah.
I'm sorry for
We're
that.
trying to guess, but
I have
it's okay.
limitations. Okay, so it was because I was writing it in point 4, but then I shifted it to first point. And I forgot to change. That should be okay, right?
Okay.
Yeah.
Solutions are in point 1, there is no solution in point 4. I give
Yeah,
you
but
That's what I did, but I wasn't sure how.
Okay, I extended the deadline anyway for 1 week, so we can do that.
Okay.
In that first, so did you understand the first problem?
Yeah.
You might have found some answers. So what did you learn? Teach me.
The divergence of the velocity can be zero accidentally, and it doesn't have a.
You're not guaranteed
Yeah.
constant.
It's necessary for incompressibility, but it's not sufficient.
You need some other.
It can be accidentally zero.
For
like,
example, a set path. If you're in a pipe, then that's enough. But you need another.
You are in a?
If you're in a constrained path and you know it's an incompressible, and you have that nabla times v is 0, then that's enough for incompressible.
That's right.
But you need
Keep
some
it as
sort
it
of
is.
other constraint.
We'll solve this equation now, but we'll discuss the outcome later. I did not understand this. I always assumed divergence of v equals 0 through this incompressible. But then somebody asked the question. Who asked this question? Did you ask the question? About
Question
the-
from the lecture that you guys.
Last, did you ask the question about
I asked
continuity
about
equation?
I told. But he asked, but I answered that.
Yeah.
That it doesn't have to be. Yeah. That you have to assume that rho is doesn't change in time in
This
order
is the
to
equation?
get the sufficiency.
So if you put divergence of rho equals 0, these two terms can arrange in the manner that it can be 0.
Accidentally, unless you you assume that rho is stationary.
Not necessary.
No, if you assume that rho
If you assume rho is
doesn't
stationary,
depend.
stationary means what? The time dependence.
If you throw away the time dependence, then you get that the rho has to be also spatially
Rho
constant,
x. Yeah, rho is a function of
and
x.
then it's efficient.
So did you think of any physical example of this?
Uh,
Physical means you may have got there are many mathematical solutions you will obtain. Okay?
Yeah, I just.
Do you see around you wherever? Do you see any example in nature where divergence of v is okay?
specifically in nature, can it be
Yes.
something constrained? Okay.
Yes, even if divergence of v is 0, still it's not necessarily compressible or the other way around.
You can take a special case of like
Function of
this
x.
const,
Okay.
and
Show me the problem.
just a second. I have the solution. Here the solution looks like that. If you take Vias constant, you can find the rho's.
Rho is a function of x.
Yeah.
Okay. So what's the
No, rho's function of x is the.
what is the function of x?
No, that way it's not the solution that it will give you. Wait. Yeah. That's the
I think
fourth
I-
section.
The fourth point.
It's
I
not,
gave you.
Yeah, I talked about that.
Okay, that is general. So you in general solutions you will get set of solutions and some good insight, but in fourth point, okay, you got the exponential one.
That was my solution.
Okay, got that. There are exponential solutions I obtained too. So there are, but I'm not sure if exactly this is what I have to see. But it might be correct.
Okay.
In fourth point, I gave you a very simple solution. Put v equals 0. This equation should be valid for all v, even if v is 0. When you put v equals 0, divergence of v is anyway 0. Okay? And this term is anyway 0. And if rho is a function of x, del rho del t is 0. So it is satisfied. But rho is a function of?
Yeah.
What it means? Means you take a box. And I asked you what is inconsistency in this. If rho is high here and small here, is it stable? And we put v equals 0. Because density is higher here,
Should be diffusion.
diffusion.
Yeah.
Density is higher.
Unless you have some boundary here, some
what did you call?
constraint, then it's
We'll
unstable.
talk about the
Because
constraint.
you
There is
take a
no
static
constraint.
case where nothing can move, there's no motion, and so if there's a difference in the concentration, in the density in different
Regions.
so nothing can happen because it's static. It's just
Diffusion means what? It will move. Right?
Yeah.
So now V is not 0. Okay?
You can have a uniform system where everything stays stationary.
But then rho is not dependent on x.
There is gravity.
you have to constrain it.
We'll
in
talk
a
about
way.
that.
Like
Here
put,
it's without he's
a boundary.
inside. Okay. So in general system, it will diffuse. So system will not remain static. But there is another situation, the atmosphere. You see around the Earth, the density changes, system is static. Now there is no diffusion because gravity holds it. In the equation of continuity, there is no gravity. So it still works. So atmosphere is the perfect example of this condition. Even if
So,
there is
in presence of gravity or another external force, there
you
will
can
be
put
no
any external force
inconsistency.
because gravity, what we see in front of us, so we can see the system. So even if divergence of V you put 0, there is no V, still this rho may have dependence, okay, on x. So it's, and air is not incompressible.
The
No.
pressure gradient have to be constant.
Pressure gradient can be anything. But here we have only density.
When V is 0.
When V is 0, you have gradient in density, you will have gradient in pressure too. But here we don't care about pressure. Pressure also changes in atmosphere, but here you only care about how the density changes.
So where is the inconsistency?
No, in gravity there is no inconsistency.
Oh, with gravity.
In simple system there is
Okay.
inconsistency.
Yeah,
It will
okay.
diffuse. If you remove gravity, what will happen?
Will,
If you remove gravity,
V
suppose,
will not be 0.
the air will go up. Right? Means there will be diffusion from down to up. It will diffuse.
Yeah.
When you diffuser, but if you put external force, it still works. So what we learned, divergence of V can be 0, but system does not necessarily have to be completely incompressible. Okay, this is a new learning. There are other situations here. This is why I designed this question. There are other cases. We will deal with shock waves in one of the topics if we have time left. It is a shock wave, compression wave. It propagates. So requirement is V is 0. A wave passes by. When the shock wave passes, it just compresses the fluid at all points. Okay. So the density is not a function of time. It's at a particular space. Okay. In that case, we'll talk about it in that case where in a particular wave solution, you still get this kind of condition where the compression takes place, but the fluid is divergence of V is 0. So these are a couple of physical examples. Okay. So today class ends at 6 o'clock.
Yeah.
If you want to take a break, we will take it now. Otherwise, we'll finish this one
How much longer do you estimate the lecture time?
until 6 o'clock. What time it is?
5 minutes to
5.
5, yeah.
Okay, it's 5 o'clock. Okay. So whenever you want to take a break of 10 minutes, you don't complain that later on that we didn't understand.
Okay.
Okay. Maybe it will, let's say 15 minutes. Okay. Take your time.
Okay, thanks.
Okay, so we obtained the wave equation that the speed of the sound is given by no. This. Father, did you get the answer of did you get the answer of the question? The answer for it? You asked the question last time.
Oh no, you didn't give me the answer yet.
Okay. So it was straightforward, like you have energy expression like this.
Yeah, I know. I remember what I asked.
You got that?
What's the answer?
Okay. So energy is like half mv square. Okay? Now v is a vector, but a square is not a vector. It's v dot v. Similarly, that's a tensor square. So when you square, you sum over all the indices. it's a square. We didn't see it properly. It's a square. It's not tensor. It's similarly like there's a vector square.
Got it.
All right. And in the expression we saw now, this f a r or something, a r plus b by r. Actually, at v r equals to infinity, the gradient of that has to go to 0, right? So the gradient of this is a. This is why only the terms r squared, r cubed, their coefficient will be 0. You'll get 4 terms here. I forgot that. Okay? If you solve it, you got 4 terms here. 2 terms go to 0 because power more than 1 will go to 0. Okay. So this is the speed of the sound. But this does not tell us how far the sound propagates in air or any medium. So we can solve it for typical cases, in the case of normal air. Okay? Ideal case. This is gas law, ideal gas law. Rho is density, R is gas constant. Mu is mean molecular weight.
What does it mean?
It's mu. It's mean molecular weight. For hydrogen or atom, it's for molecular hydrogen it is 2. For helium it is 4. Depends on how heavy gas is. It's constant. If for any particular gas, if there are many components, all the fractions are added and then you get the average molecular weight. Okay. So we use a thermodynamic relation. At constant entropy equals at constant temperature. Adiabatic system, you will study this in thermodynamics class. For adiabatic systems, this is the derivative of pressure with density at constant entropy is equal to the derivative at constant temperature multiplied by this Cp by Cv, which is the ratio of specific heats at constant pressure and constant volume. You are studying thermodynamics in this course, in this semester.
We are studying, this semester.
Either this has come or it will come. Okay.
It will come.
It's for adiabatic systems. Okay. So this del P del rho from here, it's simply at constant temperature. Del P del rho at constant temperature is rho R over here. From here.
Shouldn't it be K Boltzmann instead of R, because we don't R, because the density is not defined as moles.
It's R by mu. So if you write it in Boltzmann's constant, it is P equals to NKT. It's simply density.
That's because you use.
But if you use the density with R, it has to be in moles.
But
Yes.
you use relative mass. It's relative mass. It's not the exact mass.
It is not the mass. It's mean
So
molecular weight.
you can enter it
It
into.
is just number.
So you can enter it into okay.
If it's helium gas,
Fine.
mu is just 4. Okay. So if you use Boltzmann constant, this is how I write it, NKT. Where N is number density. If it's a single gas, it's a rho by L. Or,
Yeah. Okay.
okay, got that.
It doesn't matter. I thought that M marks the mass, not.
It's not M, it's mu.
Yeah, mu.
It's mean molecular weight.
That is the mean mass particle, but it's not.
It's not, it's just number.
Yeah. Okay.
It depends on constituents. Okay, so rho r by mu. When you put it in Cp by Cv, put it here, simplicate it like Cp by Cv is gamma, okay, adiabatic index. Has it come? Not yet, but it's adiabatic index. It's the ratio of specific heats at constant pressure and constant volume. Sorry, just a number. It depends on the degree of freedom of the gas. If it's gas is relativistic, it depends on how relativistic the gas is to temperature, etc. So this is gamma. So this is c square. This is c square. So the speed of sound turns out to be square root of
Shouldn't it be T instead of rho?
T is there.
Yeah,
So
no, rho. Everywhere.
Yeah.
okay. No, instead of rho.
Yeah,
is
instead of
going
rho.
to be-
And there and there.
Yes, it's temperature. Okay. So that's it. So the sound speed depends on what? Mainly only on temperature.
Temperature, yeah.
So if the temperature is 40 degrees centigrade and the temperature is 0 degrees centigrade, let's say 10 degrees centigrade, how much the sound speed will change?
Like factor of 20. Set from 0 to 40,
10 to 40 degrees.
10 to 40.
10 degrees
okay.
centigrade,
32.
40 degrees centigrade,
Ah, you didn't say 0. Okay, so
10 degree.
2. Yeah, by factor of 2.
But it's
No,
absolute
it's in
temperature.
It's in Celsius.
It's
Not
Kelvin.
It's not
so
there.
Oh,
you can't
Kelvin.
use
Yeah.
Celsius.
Let's
Oh,
say
it's Kelvin. Okay, so it has to be.
for one moment when I was writing notes, I also thought the same thing. The sound speed will change twice. No, it's Kelvin, okay? So
Yeah.
it changes just by, let's say, 4% or something if you calculate. I will put one problem in assignment, okay? So basically it's temperature. Sound speed, square root of temperature. It also depends on, but it depends on mu. Depends on how dense the molecules are. All right. Wait a minute. The sound, this is for gas. When I'm talking, you're listening, the sound is propagating in gas. What about water? In gas, I put the density perturbation. Right? Water is incompressible.
Yeah.
But
And-
when you know swimming,
What?
when you swim inside water, you can hear the sound of people who are talking outside. And sometimes you can hear it louder than what you hear outside, unless the water is turbulent or something. But how do you hear? Means sound can propagate in the air because air is compressible, density is perturbed, but then it goes in water. How the sound can propagate in water if the density doesn't perturb? Sound is incompressible.
It doesn't.
It does.
Somewhat
I
does.
think.
The sound not only propagates in water, it also propagates in solids. It's very loud. You hear put some stick and then let somebody take it and you hear it. It's like doctors use the stethoscope.
Yeah, and so you can describe it with funnels.
But it is,
Yeah.
but when you check the speed of the sound, it is not very much different. Slightly it changes, but not 10 times better or something. And still it is described in the similar magnitudes. So what's the difference? I answered it partly in maybe first or second lectures.
I think
The
maybe
amplitude.
water are not.
The amplitude. There will be a difference in that.
Amplitude, that's what the doctor can hear the stethoscope much louder, that means the amplitude is preserved. It's louder in solids. I think it is louder in liquid compared to gas, we have to check. But still, the basic mechanism is still the same. The question is how sound can propagate in water and
I
solids.
think that water are not entirely incompressible.
Yes.
And there's what matters here is only the difference, the perturbation.
Yes.
So it's mainly incompressible. It's almost always the constant value, but it can still change a bit, and that bit is what.
Slight change is enough because the perturbation we took already very small. It's minute perturbation. So outside, if the air is perturbed a lot, in the sound, in outside it can become non-linear very quickly as well. But in the solids, it will not. It is even. This is why in the stethoscope. Again, we have to check whether in the stethoscope. I think they have wire in the stethoscope. It should be propagating in solid. So when the doctor hears it, he hears very clear sound of your heartbeat. That's what he wants to hear. Once he hears it very clearly, because in the solid, the non-linearity is even less. It's very regular atoms. So it is still the perturbations, propagations, same density and pressure perturbation. But in solid, what do you mean by density perturbation? When I speak, acoustic waves fall on the solid surface, atoms are slightly perturbed. Very little, negligible even, but they are slightly perturbed. So the density in principle increases, but our assumption is maintained. It's much smaller, and then this propagates through the solids and liquids. So it's same mechanism. We covered everything. Okay, now let's solve this. There are different ways of solving this equation. Sometimes people solve it using series, infinite series. We use a very simple way of solving it. And as I said, this is a general equation. You will get it in mechanics and electrodynamics. So the solution is very general. Same in all. Just that this phi changes into B in magnetic fields and electric fields A, and in other ways with similar amplitudes. So let's change the variables. I define two variables, xi and eta. X minus eta, x plus eta. Just define two variables. What variables I have here? T and x. Basically, we have to integrate it over time and space. Now we define two different variables. But we have derivatives of time here, del square del t square. This del t. What is del xi del t? Let's do it x. Okay. What is del xi del t? Minus c. Minus c. And plus c. We have del square. This is simply minus what is del z del x? It is 1. Okay. Del eta del x is also 1. So this is simply and then square double derivative basically. So we put this and this, operate both of them over phi, use this equation first time. Del square minus c square Did I make a mistake of sign here? Okay. So this goes to this cancel. This cancels, but this does not. So we are left with minus 4c square 0. And then 4c square goes quasi 0.
You take derivative of phi with the function phi.
And in the last line too.
Oh, right. Okay. So basically what we are getting is the second derivative is 0 of sine eta. There's a reason why we write it in this. Now we can directly integrate this and get the value of sine eta. So this says this is what we have, and what this means is del phi over del eta equals to constant. Constant of what? It's constant function of xi. Okay, it's constant in eta. Integrate it further. Okay, so let's write it like this. This is a function of eta. I can write this as a function of xi, integrated over eta. So what you have is for this capital F. So we got the solution is two functions of xi and eta. Now put the values of xi here.
Wait,
Yes.
why do you not the function of after integrating you should have eta times function of
It's just integrated over eta.
what does it give you?
It gives you two separate functions. One has to be an explicit function of psi. This is why we separate it. It's partial, right? It's
Yeah,
not,
but how do you integrate it? over
because this is not a complete integral, it's a partial integral. So when you integrate it over eta, it turns out to be a function of xi.
Okay.
This is why you obtain this partial double derivative. So the solution says that the final function has to be two independent functions of psi and eta. The way we defined x minus ct, x plus ct, what it means is, what this means, x minus ct and x plus ct.
Traveling points.
X minus ct is traveling along x. Suppose a car, two cars are moving. One car sees another car. There's a relative speed between them. The difference of the speed comes from ct. They are moving in the same direction. But then when they are coming in opposite direction, the speeds added, x plus pt. Speeds, yes.
I did still don't understand. Shouldn't the integral of d eta should give you eta?
It comes because of its partial. This is why it's properties of partials. But if something is missing, I'll check it. But it's partial integral. This is why it is considered to be. When you integrate over eta, it has to be a function of xi.
You can say it's a function of xi because eta and xi are dependable on what to. We can find dependence.
Eta and xi are dependable from each other. Eta and xi are defined to be independent variables. They depend on x and t. Okay, I'll check it, but I think it's a property of partials. We'll talk about it, okay? I'll see if I'm missing something. Okay, I'll answer it in next class, maybe. Okay. I think it's a property of when you integrate the partial derivatives, so you get two independent functions come with xi and eta, then not it. What I was saying? Okay, so these are two waves. One is when I perturb the system, where does the perturbation go? What it says. There's a reason why we defined it in two specific form. It means the perturbation goes in all directions. If it's one-dimensional system, the perturbation can travel in x and can travel in minus x. So two solutions actually show it's positive x, negative x, towards x minus x. If it is between two walls, the perturbed system, what will happen? It will generate standing waves, keep on oscillating back and forth. Okay?
I see why it's not like that. Because in the beginning you take the derivative of psi and it's 0. It means that the solution shouldn't contain psi, so it's a function of eta. It means that f1 is
from here.
Yeah. It means that f1 is a function of eta.
F function is a function of xi.
No, it shouldn't be dependent on psi, so it should be a function of eta.
F1.
Yeah, because it's independent of psi. You take derivative of psi and it's 0, so it's.
Yeah, it should be a function of it.
This should be eta, right?
Yeah.
So now this is a function of eta. Okay.
And then similarly this is.
Okay. Okay, so we made a mistake. So this all is a function of eta now.
Yeah.
Okay. So this is basically F2.
Yeah.
Alright. Okay. Where was I? Traveling waves in both directions. In 3-dimensional waves can travel in all directions, but in 1-dimensional wave can travel in plus x and minus x. Okay. So it has to be two functions with two propagating waves. Now, waves are typically oscillations. What kind of solutions these F1 and F2 have to be in order to satisfy these equations?
What the are you asking what the functions should be?
Yes.
What type of function?
We understood that function has to be like this. Okay, function is
How many?
how many? It's periodic because the perturbations are periodic. When you put small perturbations, they have to be periodic. Not necessarily, but we will see that when you take the periodic solutions, they satisfy the equations. Any solution that satisfies this equation is a real solution. When it satisfies boundary conditions, it's a physical solution. So if you take this phi, okay, it's a general solution. Cos is periodic, and k is a wave number. If there is a period whose wavelength is lambda, then define the propagation constant like this. So this n is the propagation direction. Here it is xk. Omega is angular frequency. What is the frequency of the oscillations? So put this solution there, it satisfies. Take the double derivatives with time and space. So this is general solution of sound waves. It has complex solutions too. Alpha is some phase. It can be zero. It's a general solution. Alpha can be zero as well. What phase it starts? If you put x equals 0, t equals 0, for example, if there's a box, this is, let's say, x equal to 0. So if the wave starts from here, alpha is 0. But if the wave starts from here, like this, then alpha is some finite value. So it just depends on boundary conditions. If you take the real of this, you get this cos solution. So you put this function or this function, both functions satisfy wave equations. Physically realizable one is the cos one. You can practically assume it's a periodic wave. Okay.
I think you should remove alpha from the second equation because you have complex amplitude. I mean, the 18.
So in complex alpha will not come.
Why there is a tilde over 8?
What?
The amplitude?
Yes.
You do like yeah. Why? What is this?
It can have both. It can be complex. It can have real plus complex values. When you take its real part, you have the real. This was just in generalized way I wrote it like that.
This is the phase. I mean,
this is amplitude. This is the phase. You're talking about alpha or A?
But if the amplitude is complex, then a part of it is the phase.
Yeah.
You can take a value and phase for it. Like
A equals e to the I alpha.
You can take the complexity out of it into the exponent.
So you mean A tilde is A?
No.
What do you mean? What do you want to say?
A tilde is e to the I alpha. So when you do a
right. Okay, so this comes out into, but that doesn't matter. If you open it, it will anyway come out.
Yeah. But if you put the alpha separately, then you don't have the amplitude to be complex.
In that case, you remove it from here, remove it from here. That's what you mean.
No. You can have either of them, but both of them together are unnecessary. Only one will be sufficient.
So if you take it out, e to the power I alpha.
Yeah.
Then you have
no.
And that will be real. It won't be complex.
Oh yeah.
Yeah, that's fine. So what's the confusion?
But when you write A tilde, from what I know, it means e to the I alpha. So you just remove the alpha from the argument of the exponent.
You mean here?
Yeah.
You mean when I write tilde here, I don't need to write delta.
Yeah.
Fine, doesn't matter.
Okay.
It's just for the generalization. Okay. Alright, so we solve the sound wave solutions. Next we talk about its properties. Whereas you stand on the mountains and you shout that the sound is reflected from the mountain. Right? So it is reflected exactly like what light does. The solutions are perfectly general. Even in the light waves are reflected from the glass. Because the solutions are general, the same way, the sound waves are also reflected. So all the properties of the wave which are shared by light, electromagnetic waves, they are shared by sound as well. So we will study about some of the properties of this, let's say, reflection. And also, as you know that, okay, when I perturb the system, what I do? I induce some energy. When I speak, some energy is coming out of my mouth, which is perturbing the system. When I say the sound is propagating, that energy is actually propagating. When you put the stone on the bottom, falling of the stone gives it some energy. The stone has some energy, but once it falls in the water, it slows down. Right? So where did the energy go? If you put a stone falling faster, you notice it when it falls on the water. Inside the water, it falls down very slowly. So it loses its kinetic energy. Where did the energy go?
So the waves.
The energy is causing the perturbation. Perturbation has its own energy. That energy propagates in the way. Similarly, when I speak, I perturb the system, I induce energy here. That energy propagates here as well. So the sound waves propagate having some energy, and they show all the properties of this typical waves that you are familiar with, like light. So in next class we will discuss about its general properties and the energy propagation in sound. That will finish it. Okay? Okay. Call it a day. Questions?
About the waves in
Yes.
in liquid like water.
You mean sound waves?
There are two kinds of waves, I guess. Because when you throw a stone into the water, the waves doesn't go as fast as the speed of sound.
That's not sound. Okay,
Yeah, of course.
Let me clarify this. When I talk about the falling of the stone and created, these are waves, but they have nothing to do with what we are discussing here. Okay, those are called gravity waves, and those are transverse waves. It's just an example of waves, but the solution of those waves is exactly simple. You see cosine, right? It's fine. That's not a sound wave. But when you put the water, the stone, it creates some sound. That sound propagates inside the water. That is precisely like this. It has to be clear. Yes.
Will we also analyze this mechanical wave?
Which wave? And many.
Sure, of course, both some mechanical. I mean, the transverse wave.
Which transverse wave?
On the surface of the water.
Yes.
So we will also analyze this in the future class.
Yeah, along with Kelvin-Helmholtz. Is it in the syllabus? Kelvin-Helmholtz and gravity waves. If it is written, we will talk about it. Yes. But those are not sound. Just to be clear. Yes.
Can you explain again, please, why sound propagates stronger in solids?
Solids and liquids. Right?
Yeah.
So in air you understand, because the air is compressed, sound propagates. But our assumption is that the perturbation is very small. In the solid, atoms are packed, highly packed, they are not fluid. So the perturbation, we picturize that it does not compress the atoms. Okay? It does very little, but you can think about it that in gas I perturb, the perturbation is significant, so it propagates. Your question is, in solids when the atoms are very well packed, why the perturbation causes it to propagate, right? That's the question. It's simply energy conservation. You put up small energy, where will the energy go? The perturbation is anyway very small. So this, whatever the condition I wrote about density and pressure, the small density gradients are caused by the perturbation you cause. It is exactly the same. The crystal is deformed. Basically what you see is the crystal of the solid is deformed by the energy injection of the sound. The deformation is negligible. That's okay. The deformation is anyway much smaller than the original system's properties. That perturbation, besides being very small, it propagates exactly like a sound wave. Those pressure waves propagate in solids too. You cannot see it by eyes. You can see the propagation in gas, maybe. If it's colored gas or something, maybe you can see oscillations. In sound, you cannot see them, but the process of propagation is exactly the same. Okay. In liquids too. Liquids have, if you increase the pressure from 1 atmospheric pressure to 2 atmospheric pressure on a liquid surface, it does not compress, but the compression is, I think, 0.014% or something. It's very small compression, but it has some compression. Similarly, like solid, liquids also have some small compression. They propagate exactly in sound. I believe that in water, the propagation of sound wave will be smoother compared to gas, because in gas, the non-linearity is caused very easily. In water and in solids, the non-linearity does not come because it's not chaotic system. So this is how the sound is well behaved inside those systems. So it propagates better. The basic picture is precisely the same. It's a myth people think about the sound in solids. The wave does not propagate like what it propagates in gas. It's exactly the same. Yeah. But it does not follow the precise assumptions that we talked about. Did I answer all the questions that you asked in the last class, including the energy tensor? If I forget something, just remember, but I think I did answer. In third question that we did in the class test, we got last term eta multiplied by 0. And the interpretation was, the conditions are, the question was, can you interpret the density, viscosity with that? You wrote the answer correctly that it cannot be interpreted. But I said once that means the viscosity is 0. It is not necessarily true, because viscosity, because even if the last term is 0, you remember third question? No. The last term was 0, eta multiplied by 0. And what it showed that if last term is 0, the equation follows, the system follows Euler equation for invisible flows, which it looks like it should mean that viscosity should also be 0. But it is not necessarily true, because it depends on the system's conditions. The conditions that were given, they make the last term 0. It does not necessarily mean that the viscosity is 0. Simply it means that from the given conditions, viscosity cannot be determined. Okay? You could listen to me from here. Did you understand? I told you. Okay. Done? Thank you.
Thanks, Moksh.
So there was a question about, this was clear?
Yeah.
Okay, this is clear.
Can I ask something about thermal?
Yes. Talk about the first question.
Partially to the gas. Conversions for rho and velocity. Something like this.